This episode is brought to you by Brilliant. Benjamin Franklin once said, "He that can have patience can have what he will." And when it comes to space, it means having a lot of patience, but the reward is an entire galaxy. So science fiction often shows us faster-than-light spaceships taking pioneers to new colony planets halfway across the galaxy in mere months. And on the show we often discuss how FTL probably won't be an option, but we can still colonize space. It will just take us longer, requiring generation ships that might move at 10 or 20% of light speed, needing a generation or two to get to the nearest stars and maybe several to get to a preferred candidate system. However, while known physics certainly allows such ships, it relies on a lot of optimistic solutions to problems, not least of which is if it is really possible to build a ship that could survive moving through space at truly relativistic speeds. What we normally do on this channel is to show everyone that even if we don't get the FTL technology as ubiquitous in science fiction, we can still colonize our galaxy. Today, we'll take that a step further and argue that even if we can't travel through space while moving at a mere 10% of light speed, we can still colonize the galaxy via slowboat ships, what we will call Crawlonizing, and we'll also discuss how that might vary in approach. First, we need to talk about why we might not be able to go faster than 1% of light speed or maybe even 0.1%, and there are a number of reasons this might turn out to be the case, either hard limits or simply a matter of practicality for big colony ships. For instance, we might be able to send probes or scouts to systems far quicker than we can a big colony ship, also called a slowboat at these speeds, for a combination of risk and cost. A robotic probe or 100-ton scout carrying a dozen crew members simply doesn't come with the same cost and risk as a 10-gigaton O'Neill cylinder designed for carrying 100,000 people and an entire ecology. That slowboat needs 100 million times as much mass and fuel to speed and slow it, and it's carrying families in a community, not a handful of intrepid explorers who knew the risks, or just a computer who fears no risk. Even ignoring the rocket equation, which is even harsher in cost for adding speed, a ship moving 10 times as fast needs 10 squared or 100 times the energy or fuel, and one moving 100 times faster, 100 squared or 10,000 times the fuel. We can make a very strong case for why this is no real limit on colony ships, since that fuel is often assumed to be either hyperabundant hydrogen or deuterium, but that does assume we have gotten fusion working, or at least deuterium-deuterium fusion, and small enough for a spaceship. We don't have profitable fusion yet, and maybe never will. What's more, because a fusion reaction still needs to convert that energy into thrust out the back of a rocket ship made of real materials so that they don't all melt, maximum speed might be lower than the mass to energy conversion of fusion implies. I've heard folks question if we can achieve a better exhaust velocity than perhaps 50 kilometers per second with a fusion reaction, hundreds of times less than the mass to energy conversion rate should give us. Now I think we can do way better, but realistically, if that were the limit, that puts us at about triple the exhaust speed, 150 kilometers per second, as a maximum ship speed, from thrust alone anyway. This is a touch slower than the Parker Solar Probe got to as it accelerated toward the sun, with gravity assisting, so don't think of this as a super sci-fi velocity. 150 kilometers per second is very fast, but the speed of light is 2,000 times faster. We're going to be talking about ships in this speed range to about 20 times faster, 1% light speed, and for context, 300 kilometers per second is 0.1% light speed, and 3,000 kilometers per second is 1%. We often abridge kilometers per second as kms. I am not worried about being able to get to 0.1% or 300 kms from a propulsion angle. This is a limit induced by an assumption we might find the engineering environment too harsh to make ships able to go faster, or that some other unanticipated constraint might come in. Plus, we have too many tricks for boosting speed, like slingshotting around planets or stars, or accelerating the ship with lasers and using the fuel to slow down, or even a light sail on a close approach to the destination star. A lot of those tricks don't work as well at significantly higher speeds though. As an example, your classic solo sail, slowing your ship, is all about the power the starter is using is putting on that sail, and how long it can do that, and if you are moving fast, that time is decreased. On the other side of things, the energy of various little collisions of gas and dust particles with a sail is massively enhanced by moving faster, with a drag force whose power rises with the cube of your speed. So a ship might leave a system using laser propulsion on a sail, run itself on a nuclear engine as it heads out into space, and then use its sails again to slow on gas particle collisions as it nears a system, and let the solar sails or mag sails finish the job of bringing it to a halt around its destination world. There seems to be a strong consensus we can achieve at least this 0.1% or 300 kms speed, so we will use that as one of our cases today. Getting above 1% though is a bit more debated, and a lot of that is because of those gas and dust collisions rising in power with the cube of speed. See, the kinetic energy of an object rises with the square of velocity, but how often you smack into stuff along your path rises with your velocity too. So if you go 10 times as fast, you hit stuff 10 times as often, and each thing has 10 squared or 100 times the energy, so 10 cubed or 1,000 times the power. Now you've probably heard before that even running into a tiny grain of sand in space will rip your ship to pieces, and this is almost entirely hyperbole. For one thing, grains of sand vary in size and mass by around a factor of about 10,000, and generally for a given square meter of spaceship front, you would expect to disturb something like a single grain of sand in collisions between a pair of stars. Space is pretty empty, some parts emptier than others, and the variance in density of interstellar dust and gas is a lot like the variation in sand grain sizes. Part of that hyperbole is about speed, but a lot is from ignoring that most grains of sand are the tinier ones, and most parts of space would have the thinner ones. Colliding with a small grain of sand, say a microgram grain at 300 kms, again 0.1% of light speed, is releasing 45 joules of energy, a little less than a typical tennis ball would be carrying. Though slamming into a spot only a micrometer wide, so that spot is taking real damage, and bear in mind that a 1 microgram particle is in the lower mass range for interstellar dust. We can build the power of the spaceship to handle that level of damage, especially given that it is not constant, so plates on the front can get dinged up and can be removed, repaired and replaced during flight. Alternatively, a big grain of sand weighing 10 milligrams and moving at 86% of light speed, 260,000 kms, has 900 billion joules of potential energy in it, 20 billion times the energy involved in that previous collision, and is equivalent to about 215 tons of TNT. Needless to say, that's going to hurt, and that is something you're likely to run into with the front of a decently sized spaceship during an interstellar flight. Again, space is empty, but not that empty. The handy thing about moving at 86% of light speed is that from your perspective, the trip is going to take half as long, from relativistic time dilation, on top of your conventionally higher speed. So a trip taking 1,000 years at 300 kms, which is only a light year, is taking that ship at 86% of light speed just over a year, but their own relativistic dilation would make them think it was only about half as long, about 7 months. Obviously that is preferable, but since it involves spending millions of times more energy, at best, and getting hit by what are effectively large bombs along the way, some of which are nuclear in scale, it's a bit more iffier process both in terms of economics and engineering. You also have way more detection and response time if you see a bigger object, like a space rock the size of an actual tennis ball, to see it and either dodge it or vaporize it. Even seeing and responding to a rock that small at 300 kms is pretty tricky. That's a speed that's about 1,000 times faster than a plane travels after all. So giving yourself 10 seconds to spot and react to such a stone means seeing it 3,000 kilometers or 2,000 miles away. And remember, this is something the size of a tennis ball. That's as far apart as West Coast cities like LA and San Francisco are from those of us living around the Great Lakes, and is the distance you need to be able to detect that tennis ball at. And for a little more context, hitting a tennis ball-sized rock at 1% of light speed is still going to be a couple trillion joules of energy, depending on what the tennis ball-sized rock was made of and how it hit. A bit more than the relativistic grain of sand of a moment ago, though maybe still survivable for a big ship with a big thick forward prow. So things get pretty iffy at speeds above 1% light speed just for moving through space. One bit of good news for folks who aren't fond of calculating in relativistic effects is that relativity is pretty minimal at this scale. You cannot ignore it at an engineering level. At 1% light speed, your clocks are going to be off by 4 seconds a day, and that needs to be factored into your positioning and so forth. But it can be ignored when calculating flight times on such by you or I, and 0.1% is even less, about 43 milliseconds a day or 16 seconds a year. Of course, that definitely means you're not getting any time savings on your flight for the passengers when you need thousands of years to save even a day from relativistic effects. And this takes us to our first key notion: time is the biggest factor in decision making at these speeds. I have often suggested that we're not likely to be skipping around orange and red dwarf stars, and instead looking for much rarer yellow twins of our own sun, or bypassing systems that lack an Earth-like planet. This seems even more true if it takes 2 or 3 times as long to get to the nearest yellow star, if a red or orange one happens to be closer. As a reminder, these are all white stars anyway. The red, orange, yellow, blue, or white designations just discuss where their peaks are at, and even a comparatively cool red dwarf varies from our daylight in that it's the same color as traditional incandescent bulbs are. You can definitely notice changes in color, warmth, and tone, especially in blue shades with incandescent lighting, but not to the point of it being a major quality of life concern for colonists under red suns, especially given that they can use daylight bulbs in homes or stores. A person contemplating setting up a colony around a nearby red dwarf like Proxima Centauri or Barnard's star at even 1% of light speed versus Tau Ceti, the nearest yellow star besides Alpha Centauri and our own sun, is looking at more than 600 years more travel to get there at 1% light speed and 6,000 years at 0.1%. 600 years is a long time, longer than even the most generous estimate for the industrial age, and 6,000 years ago predates recorded history and enters into the realm of pure archaeology. Of course, simply contemplating journey timelines like this makes one wonder who would volunteer, even if we were using hibernation options like freezing people, which is a technology we cannot take for granted will be developed, and as we note in our Sleeper Ships episode, generally requires parallel technologies to what you need for radical life extension technology too, and longer lifespans also alter the colonization dynamics. Now, for my part, I don't see that as preventing things. Fewer folks will volunteer for such long voyages, but since the entire colonization timeline is slowed, you have a lot more time to recruit in. Just as an example, a colonial mission initiated in the year 2200 AD, meant to get to Tau Ceti and planning on taking 1200 years, crawling out at 1 light year per century, might opt to freeze its colonists, and it might take a few decades to get the final funding and the ship built too. So volunteers and early investors might all opt to freeze themselves to be loaded when the ship is ready to depart, and so when it leaves in 2222 AD, there might have been thousands of people frozen for the trip, but only 100 or so from any given year from 2200 to 2222. Tau Ceti is also only 11.9 light years away, not 12, and suddenly that makes a real difference because it is an extra decade of flight time. At our lower speed limit, 0.1% light speed, that jumps to a century being shaved off of a 12,000 year trip. We have spent centuries building things before, so I'm not worried about finding funding or volunteers, even if I would not expect the same kind of deluge we would get in some other scenarios. Those sorts of projects tend to be things like cathedrals, and so a similar degree of group devotion might be needed, but that implies a parallel source, like the Mormon colony ship we see in The Expanse. And if we just assumed every medium-large nation and religious denomination decided to fund a colony mission at some point, that is around 100, enough to get one to every star within 15 light-years of us. And now we need to contemplate that the trip time to reach such a colony is similar or even longer than what we need for that colony, once established, to grow that colony to be as populated and powerful as the homeworld that sent them was, so that they might consider sending out colony ships in their own turn. If you need 1,000 years to get to your new homeland with your colonists, and 1,000 years after colonization you have an interplanetary empire of billions there, then you are probably contemplating sending your own colony ships onto any uncolonized neighboring systems. Given that this is a founding piece of your history and culture, it's probably been a prized goal for centuries. You are descended from a race of explorers and pioneers who settled your world. It's built into your culture and maybe even into your DNA, and when folks suggest building a next wave of colony ships, naysayers are likely to have people point at the ground everyone is standing on as proof it can and should be done. And this argument will hold a lot of weight with those present, maybe even beyond what rational thought would permit, as it is baked into their culture. Many centuries later, on a star around a world even further from Earth, that same conversation is likely to replay again, leapfrogging through time and space to the galactic rim and maybe beyond. So when estimating the speed of galactic colonization, FTL colonization tends to require long incubation periods for growing your numbers before you want a new colony when compared to your travel times to get there. However, Crawlonizing the galaxy is all about travel times, not incubation times at each colony as you leapfrog outwards. I would say that you could comfortably estimate when contemplating colonizing the galaxy that the rate that occurred at would not be less than half your typical colony ship cruising speed. Indeed, as we'll discuss in a bit, probably actually less than that cruising speed, but at half the speed, assuming folks spend about half the time traveling and half the time incubating at the new colony before sending out seeds. A 1% lightspeed cruise velocity colonizes the whole galaxy in about 10 million years, and a 0.1% in 100 million years, and the galaxy is estimated to be over 10 billion years old. Indeed, Earth itself orbits the galaxy in about 230 million years, what we call a galactic year, so even an extreme crawl at Voyager 1 speeds, you can get a galaxy colonized in a timeline a bit longer than our orbit of the galaxy. However, I don't believe this represents a true colonization scenario anymore. First, and we'll come back to this in a bit, there are a lot of options for speeding things up at that galactic scale by throwing extra effort into getting a few ships out much further beforehand, and doing that by exploiting options like the interstellar black hole highway network or red giant hubs, which we'll come back to. Second, colonizing the galaxy isn't just about getting to every star, because there's a lot more to the galaxy than those objects, and Crawlonizing the galaxy makes those other spots even more important. If you are flying from star system to star system at hundreds of times light speed on your awesome sci-fi ship, you don't need to stop between stars, assuming it has a bathroom and kitchen on board anyway. Conventional starflight does not encourage taking breaks either, as you coast at speed rather than having to keep the engine roaring to stay at speed like with cars or planes, burning fuel. However, while space is pretty empty, there are likely to be a lot of big rocks or ice balls floating around between stars, each a tiny potential oasis. Truth be told, so long as I've got a functioning fusion reactor, I can turn any rocky ice ball the size of a mountain into a space habitat, able to support more people than all but the largest of modern nations. Now, in our episode Colonizing the Oort Cloud some years back, we examined the notion in a little more detail, though it feels like a topic I might want to revisit with an additional episode, and so we'll do an episode on deep space habitats in a couple weeks. But for our purposes today, the key concept is that places like Neptune or Pluto or the Kuiper Belt that we think of as out near the edge of our solar system are really not even 1,000th of the way out to what we think of as the territorial edge of your typical star system. Our planet is 1 AU from our Sun, Neptune more like 30, and a light year is 63,000 AU. There isn't much matter out there when you compare it to the vastness of space, and yet there's still also an awful lot. Estimates are necessarily hazy for the outer Oort cloud, but we think ours might contain around 1 trillion objects a kilometer across or more, and probably at least 1% of those are going to be metal-rich. We also expect many billions in the larger 10 plus kilometer diameter range. Definitions are also somewhat hazy, and for instance, we have an asteroid belt between Mars and Jupiter with about 1 million objects a kilometer wide or more, which is really multiple belts. Then we have the Kuiper belt out past Neptune, which is really more of a torus or donut shape, and the scattered disk, which is more disk-like in that same general region. Then you get to the inner Oort cloud, which is also donut-shaped and sometimes called the Hills cloud now, and which stretches out to about 20 to 30,000 AU, or 4 to 6 light months from the Sun, and it is thought to contain 5 times as many comets as the outer Oort cloud. Now, there's nothing special about a kilometer-wide object. You would expect at least twice as many bodies half that wide or bigger if the distribution is anything like our asteroid belt, but there's also something like 25 million asteroid belt objects bigger than 100 meters across with a mass of at least a megaton, and any of those represents either structural material for building a space habitat or the filler to go inside as rock, water, or air. We often talk about turning our asteroid belt into a collection of artificial habitats, able to comfortably house a quadrillion or more people, and there's a lot more mass in the Oort cloud to work with, probably several thousand times as much, which isn't actually all that much. Earth itself is a couple thousand times heavier than the entire belt, depending on estimates. We usually estimate the Oort cloud has at least an Earth's worth of material clumped into usable bits, and it may be way more. What it means though is that the Oort cloud should have no problem providing the materials for housing 1 million times as many people as Earth does nowadays, if not many more. And if they've got working fusion, then proximity to the Sun or inner system still has a lot of plus sides, but also means that many of the things that would tempt someone to travel to another star system could be found just by immigrating to a space habitat in the Oort cloud. Now, without fusion, we might find it is profitable to stretch long lines of relay stations between our Sun and its nearest neighbors, possibly a long line of stations refocusing an energy beam and sending it to the next, or a mass stream to minimize attenuation. If we assumed each relay point was 12 light hours apart, 1 day of signal-apply message lag, and most of those relays were 10 light years long on average, that's a chain consisting of 7,300 stations. If we have 100 total lines, that is 730,000 relay stations. Sounds like a lot, and if those are all near-cylinders in scale for the main habitation drum of the relay station, then we're looking at anywhere up to 1 million people in easy comfort. 730 billion people in total, about 100 times the population that Earth had on the year this channel premiered, and probably in the vicinity of a few quadrillion tons of building material, which is like one largest asteroid of the kind we only have a few hundred of in the asteroid belt. In other words, we expect no problems getting material for it. Now, I mention these because once you slow crawl it out to a new star system, you can use these relays to move ships a lot faster, because you can relay power out from the Sun even if you don't have fusion generators, to use it for pushing beams, and you can keep that area a lot clearer and better monitored for space debris, allowing safer travel along these interstellar laser highways. If you don't have fusion or something better, then besides these relays, power is either coming in beamed via some extensive infrastructure and at a significant cost, or you're running a classic nuclear power plant, and that probably means much more energy compact approaches to space habs that are still running through kilograms of uranium or thorium a day. Though truth be told, that's not much of a bottleneck, as it might cost less than gasoline does nowadays, even though it's 1 million times energy richer. And again, we'll do an episode on deep space habitats in a couple weeks to examine this more. Key concept for now, a lot of what folks will want around distant planets, they can also get by mining out some iceberg floating in deep space, and a lot faster, and with a real chance of maintaining contact with people from home. What's more, a handful of colonists claiming an entire solar system, or even just a planet, is a much harder claim to maintain than grabbing a small mountain in space, less folks seeking to jump your claim or become your neighbor on the other side of the continent. Of course, you still have communications moving at light speed in a Slowboat environment, and those relays are good for that too. It also permits instantaneous teleportation for posthumans with digital consciousnesses via data transport teleportation. Their minds move at light speed and experience no time during transit. A human might teleport this way too, with their body and mind being duplicated on the other side. Now, this is really just a copy of their mind, but for many that might work. See our teleportation episode for more on that, or see also our androids, cyborgs, and transhumans playlist for discussions of the pros, cons, and challenges of digital consciousnesses and uploaded minds. What it generally means though is that we would expect the Oort clouds would be getting colonized too, and that you're probably never more than a light day away from some habitat when in long colonized regions of the galaxy, because even if we're just talking a smaller Kalpana-style habitat for a few hundred folks, or possibly for a single family that likes its elbow room, there's too many upsides to having such outposts. You would need a few billion of these per system for that one per light day density, but in the context of a Kardashev 2 Dyson swarm civilization, which are even more likely, I would say, in a Crawlonized galaxy, that's still a smaller budget item proportionally than a highway rest stop is for the US. And I mean a rest stop, one, singular, not all of them. A few billion small space habitats just isn't anything noteworthy to build and fund at the Kardashev scale, so you could subsidize their construction like crazy and even pay folks to live there and still barely notice it as a budget item compared to the inner system economy, which benefits greatly from that outer system. If you do have fusion or black hole power generators, then you don't need to subsidy them from in-system, they are swimming in reactor fuel out there. So now we have a galaxy-sprawling civilization crawling out from Earth at somewhere between 0.05 and 0.5% of light speed, and by the year 10,000 AD, you've got our whole system Dyson swarmed up and well out into the Oort cloud, and you can be shoving spaceships along relay paths to our nearest neighbors. Personally, I don't see any problem going much faster than that, but more importantly, I said earlier that I would expect that colonization wave at the galactic scale to move as fast or even faster as the typical colony ship's cruising speed, and I want to finish by explaining that. It doesn't seem to make much sense that you could colonize the whole galaxy faster than a single ship typically moves, but here's the key piece. We have 4 objects of note: black holes, neutron stars, white dwarfs, and the red giants that make them when they expand and die off, sometimes as a supernova. Now we can sundive on stars as we travel to build up more speed, much as we do with planets, but you tend to get pretty scorched doing that sort of thing, as closer is better. Indeed, you can do some pretty neat tricks diving on a star with a solar sail to expand out as you pass it, to cut down on fuel use in a slingshot maneuver. But this is easier to do around objects with more mass than brightness. That means red giant stars are not your friend for this maneuver, though they will be for another that we'll get to in a minute. Red dwarfs are better, being much less bright per unit of mass than our own sun, let alone a giant, and being the most common type of star. However, white dwarfs, the most common type of dead star, are much better for slingshotting around as they are typically around half as massive as our sun. Most current white dwarfs come from stars that were originally more massive than our sun, and some white dwarfs are more massive than our sun like Sirius B. But a white dwarf is usually only about 1% as wide as our sun and about 1,000th as bright, though it varies a lot, meaning you can get a lot closer to a lot more mass, allowing slingshots to far higher speeds. If your ship can handle being at 160 times Earth's solar illumination for a couple of days, maybe they have a nicely mirrored surface for instance, then you could be within 38,000 kilometers of such a dead star, with a star's mass for accelerating you, but without getting burned. And that's very close in, given that our sun is 18 times wider than that, and you would be flying through its core. So it is very plausible a spaceship might accelerate towards Sirius B or some other nearby white dwarf. There's several within 20 light years of us, most of which are cooler and dimmer than Sirius B. So you catapult away from this to gargantuan speeds, and point yourself toward a neutron star or black hole close to where in the galaxy you want to end up at. Now, neutron stars are much rarer than white dwarfs. We think there's around 1 billion in our galaxy, and the nearest one is 400 light years away, and the older ones are dimmer and thus much safer to slingshot around. Black holes are considerably rarer, but there's still at least 1 million in our galaxy and probably spaced out no more than 1,000 light years or so apart. Thus, you can use them to haul yourself up to decently high speeds. This works even better around binary pairs, though these are fairly rare, or even pairs of white dwarfs. This is called a Dyson slingshot, by the way, as Freeman Dyson suggested for white dwarfs or neutron star pairs about 60 years ago, and we also have the Halo drive as a more advanced version of this using black holes and lasers, and able to go faster. We will skip on further discussion of all of those, besides noting that any of these approaches allow you to boost to over 1% of light speed, indeed a lot more, though they only really help if you have one in your home system or are making a very long trip where such objects are considerably closer than your trip length, thus you go to them first. More importantly maybe, a slingshot maneuver can be used to slow down too. So you can hurl yourself toward a dead star or dead star pair, hurl yourself toward another one a large part of the way across the galaxy, and slow down at that one to speeds that your ship can use conventional methods to finish slowing down on at some more habitable neighboring system. You can also drag through a large, thin red giant to further slow a ship. Those are cold as stars go, but more importantly they are huge and wispy. So if you have a very reflective hull, then much as you could stick your head in an oven for a few moments, even though it's hotter than boiling water, which would scald you almost instantly, you can slam through a red giant's upper layer to slow a ship, and also use sails to slow using its sunlight and solar wind, both of which are immense, and then drag those sails more as you go through that star. As a result, we have a lot of options for sending ships out to some ideal hub systems that are near such stars and dead stars, and thus can travel to them faster than our normal ship speed. And given the times involved, shaving time off on these dead star galactic highways is likely to mean that this new hub world has tens or even hundreds of thousands of years of head start as a new nexus to get some neighboring worlds than ships moving at the normal cruising speed. Think of the galaxy as the surface of a pond as rain comes in, causing thousands of little ripples out from where the individual drops are falling, only these ripples are that hub system, colonizing thousands of stars bordering it, or even millions, before expansion waves from other neighbors or back home on Earth reach them. So even if we can't ever get our awesome fusion drives or FTL systems, we can still crawl our way out to the edge of the galaxy, covering it with our civilization in considerably less time than a galactic year. I think we will be able to do it far faster, at well over 1% of light speed and maybe 20 or 30%, but even if we can only go 1,000th the speed of light, we will get there one day. We don't know if we share this galaxy with other life forms that are not from Earth, but if we do not, then the whole galaxy is ours, and we do have the means to claim it. Admittedly, it is going to require some patience and determination, but as Samuel Johnson said, great works are performed not by strength, but by perseverance. One thing missing from a lot of our discussion today was looking at how probability simulation might let us determine how successful or rapid galactic colonization occurred at various speeds of travel, terraforming or habitat construction, and population growth rates. We tend to limit ourselves to intuitively logical forecasting with that in mind, but it doesn't eliminate the value of that sort of simulation, and if you want an example, Brilliant has an excellent one on mission success and lifetime on Mars that really helps visually demonstrate that, along with a great course on probability in general. When it comes to math, beyond the fundamentals, when folks ask me if something is practical for them to know and use, probability is an absolute and emphatic yes. It is one of the greatest tools mathematics gives us, and it is incredibly useful in virtually every aspect of life. As an example, the actuaries who calculate risk for a living have the lowest divorce rate of any profession, followed by physical scientists. Many key life decisions benefit from being able to see the odds clearer. It is also so much easier to learn with interactive examples, and that's so often the hard part for learning math or science. The best learning is hands-on and interactive learning, hands down, and Brilliant has worked tirelessly over the years to offer more and ever better interactive learning options for math, science, and computer science. Brilliant makes it easier for anyone to learn, be it the basics or advanced materials. Life gets a lot easier if you know how to calculate your odds, and learning is much easier if you got Brilliant as your partner. And they've been a partner supporting this show and many other education-focused shows for years now, helping us make knowledge easier to get and more abundant. With Brilliant, you can learn at your own pace, learn on the go, and learn something new. To get started for free, visit brilliant.org/IsaacArthur or click on the link in the description, and the first 200 people will get 20% off Brilliant's annual premium subscription. Alright, that wraps us up for today, but we'll be back next Thursday to see what life as an interplanetary explorer might be like, as we finish up our 3-episode look at surveying habitable star systems. Then we have our live stream Q&A coming up Sunday, June 26th. After that, it is on to July for a look at deep space habitats, then extragalactic sanctuaries on July 14th. Next, we'll have our mid-month Sci-Fi Sunday episode, Primitive Aliens, and the challenges of interacting with them on July 17th. If you want alerts when those and other episodes come out, don't forget to subscribe to the channel and hit the notifications bell. And if you enjoyed today's episode and would like to help support future episodes, please visit our website, isaacarthur.net, for ways to donate, or become a show patron over at Patreon. Those and other options, like our awesome social media forums discussing futuristic concepts, can be found in the links in the description. Until next time, thanks for watching, and have a great week.